Hi, and welcome to the PhD sessions of the ViViMaT workshop. My name is Stefan Eder, and I run this show. Our next speaker is Francesc Pèrez-Ràfols, who graduated in industrial engineering from the University of Catalunya in Barcelona. He then earned his PhD at the Technical University of Luleå in Sweden, and now holds a postdoctoral position at the University of Padova in Italy. His research focuses on modeling lubrication and contact mechanics with rough surfaces. You know where to leave your questions, and Francesc will start right after this short message.
Coatings is a peer-reviewed journal of coatings and surface engineering published online by MDPI on a monthly basis.
And now, contact mechanics.
Hi, I'm Francesc Pèrez-Ràfols, and welcome to this talk within the scope of the ViViMaT typology workshop that I have entitled The Role of Viscoelasticity in Contact Hysteresis and Retraction. And this is a job that has been also carried out together with Lucia Nicola and Jenna Steven van Dokkum. And if you want to find out more about this type of work, I present these two references. The first one basically focuses on the method that we use, and the second one will contain most of the results. So just to motivate, if you're plotting contact area versus load in a sort of ball and flat contact, and you first indent the ball, it will follow this nice straight line indentation. But however, when you have indented and hold a bit and then start to retract, it will not follow the same path, but instead it will follow this other path here. And this adhesion hysteresis, of course, will cause energy loss, but has been observed experimentally in many places. And I give here just a selection of references that have studied this problem. And the thing is that there's a list of possible reasons. Viscoelasticity, of course, that's the main topic of this work, but also roughness, mechanical instabilities, molecular entanglement, time-dependent chemical bonding, etc. And the thing is that usually it's not that there's only one of these that is correct, but depending on the working conditions, one or the other will be most relevant, and probably several can also interact between each other. So in this context of these observations, the goals of this study was to characterize the role of viscoelasticity in adhesion hysteresis, but also to give a bit of an aid in deciding whether or under which conditions viscoelasticity leads to large hysteresis, so that when an experiment is planned, for example, it can be known in advance whether viscoelasticity should be accounted for or not. And so with that, let me start with a brief overview of how viscoelastic materials behaves. So we can view them in this behavior in two fashions. So first, we have this sort of this fixed beam of material, and we apply a strain in a stepwise fashion. Then, unlike in an elastic material, where you will also see a step in the stress, you instead see this immediate jump towards a very high value, and then a relaxation towards a finite but much smaller value. And the other way to look at it is to look at the response in the frequency domain. So now instead of applying a step strain, we apply it in an oscillatory fashion. And then we can look at the elastic modulus as a function of frequency, and it looks like this. You have a real part that's mostly telling you about the stiffness of the material, or the stiffness the material exhibits rather, and an imaginary part that's mostly characterizing the energy losses due to viscous dissipation. And in this graph, you can see that there's clearly three different regions. Two of them at very low frequency. You have the Ravary or adiabatic region. At high frequencies, you have the glassy region. And both of these regions are elastic or almost elastic in nature. And you can see that the real part is almost constant, whereas the imaginary part is almost zero. So there will be almost no dissipation. But of course, although both are elastic, they are quite different in the sense that the equivalent elastic modulus would be quite different. And in between those two, you have this region where the real part is varying a lot, and the imaginary part is quite large. And it is here in this transition region where most of the viscoelastic dissipation will actually occur. And let me finish this introduction talking about the Zener model, which is the one that we will use to model our material in this work, which basically can be described by these springs and dampers placed in this arrangement. And it can be easily shown that this arrangement leads to a behavior that can be described by this time-dependent elastic modulus. And just to quickly understand what these parameters mean, we can plot again the response to a step strain. And you can see that first at very small times, or that will be also equivalent to very high frequencies, you have this infinity, which is equal to this the sum of these two parameters, E1 and E0. And then when it relaxes, it reaches a value given by E0. And then finally tau, which is indicating the time that it takes for a material to relax, so that if tau is bigger, it will take much longer to relax, whereas if it is smaller, it will relax quite quickly. So with that, let me show the more in detail the problem specification. So basically, we're having this viscoelastic cylinder against a flat, rigid body. And the viscoelastic cylinder is going to be modeled by, as I said, by the Zener model. And as we said, we first indent it adiabatically, meaning neglecting any viscoelastic effect, until a maximum penetration H. And then from that point, we reactivate the viscoelastic nature of the material, and we start to retract at a constant velocity Vz. And then we look at the load versus area curves at varying velocities, for example. And the boundary condition we're applying is first a hard wall constraint, meaning that the viscoelastic cylinder cannot deform nor penetrate the rigid body. And then also we model adhesion through the ductile Maugis model. And this model basically establishes that there is a characteristic separation delta max, such that if the surfaces are closer than this separation, there is an attractive stress not denoted by PA, whereas if they are further apart, there is no attraction. And in this model, and in any model regarding adhesion, the work of adhesion, which is the area below this curve, so given by PA times delta max, is the most important parameter. So in this problem, there are a few non-dimensional very relevant parameters. The first one being this ratio between the instantaneous elastic modulus and the adiabatic one. That in this work we'll fix at 10 and not talk about it anymore. And then you also have the non-dimensional indentation, which basically, it's how far do we push before retracting, as normalized with the radius. And also the non-dimensional velocity, which for the scope of this presentation, you can think of it as the velocity. But the advantage of having it as a non-dimensional one is it also includes things like tau here, which reflects the fact that if the material takes longer to react, it will effectively see everything happening to it as if it was occurring faster. And finally, the Maugis parameter will also be important. And that basically tells you how short or long range is adhesion. So we could fix the work of adhesion by increasing the Maugis parameter. What we're doing is that the separation at which the surfaces feel each other is now smaller, but the pressure with which they attract has become higher. And now let me talk about the modeling approach that we followed in this study, which is using Green's function method with application to viscoelastic materials. And the overall strategy here is to first solve analytically for the pressure needed to cause a sinusoidal displacement. So you have this infinite viscoelastic half space, and you apply displacement and solve analytically for the pressure needed to cause this displacement. And this, of course, is done in the Fourier space. That's why the sinusoidal shape. And then you can use this result in your actual problem. So you have a given deformation that might be the correct one or not. But from this deformation, you can get the pressure that would be required to compute this deformation. And then using that and starting from initial guess, you can use dynamics to move towards equilibrium. And the main advantage of this is that only the surfaces need to be meshed, and hence the computations are much faster. And this can be really important in the case of viscoelastic materials because these require a very fine time step in order to capture properly the relaxation. And of course, this method was developed a long time ago for elastic materials. But it's a bit more complicated for viscoelastic materials. The great advantage we have is that we can use the correspondence principle, which states that if you have a solution for the viscoelastic material and take the Laplace transform in time, you will get a solution for an equivalent elastic material. So what we can do is to take the solution for the elastic problem and use inverse Laplace transform to obtain a differential equation on the time for the viscoelastic material, and then especially with a simple model like the standard model, you can integrate this equation to obtain an discrete formulation. So with that, before showing the numerical results, let me give a qualitative explanation of what's going on. And the first thing is that we will assume that for this explanation, not necessarily for the model, that the adhesion is concentrated just at the edge of the contact, so that on the bulk there is no viscoelastic effects, or at least that this can be neglected. And of course, we shall see also with the numerical results is a good assumption for the range of velocities that we have studied. And of course, with much larger velocities, the bulk viscoelasticity will also be relevant, but we will not discuss this topic here. So the question here is why, or how can it be that viscoelasticity is so relevant near the edge of the contact, but not in the bulk? So for that, the main or the key aspect is that because of the digital interaction between the cylinder and the rigid body, there will be formed a narrow but very high pressure spike, as shown here at the very edge of the contact. And so when the contact is receding, since this spike is attached to the edge of the contact, it will also move together with the receding contact edge. And if we look at the given point at the surface and look at the pressure as how it evolves in time, you can see that first at point 1, for example, you have a very low pressure. And repulsive because it's in contact, and then as the spike passes above it, it will also see this very quick rising and dropping of the stress, and then once it's out of contact, there will be no pressure. And basically, this sort of pattern of going up and down is going to produce very, very high stress rates that will make it possible for viscoelastic behavior to be important. And so basically we'll see a picture like this because of that, whereas so very close to the contact edge, the stress rates will be so high that the material can even be in the glassy state, and around that, say very quickly as you penetrate into the body or go away from the contact edge, the pressures will start dropping fast. So there will be an area that will be in the transition zone, and that will account for most of the viscous dissipation. And eventually the stresses will be fairly low, so that even the stress rates will be negligible, and hence the diabatic state will be the most relevant one. And importantly, and that has been done in the literature quite a lot, that what you can see, this picture is as if the ball was the same, but you have just changed the material here at the edge. And that, of course, can be viewed as a change in the work of adhesion, because, of course, this interaction of this more rigid material with the rigid body will be quite different as compared to the interaction with the material in the rubber state. And hence, we'll always be able to watch these viscoelastic effects as a change in work of adhesion from the original one given by the ductile Maugis model to an equivalent one that will be relevant for the viscoelastic. And of course, this effective one will depend on velocity and etc. And with that, we can show now that there's a couple of limits based on the explanation. So, of course, at very small velocities, the material behaves elastically, and hence the JKR solution apply for adhesive interaction of elastic bolts. And here we plot that in this sort of axis where you have load versus the square root of area, or contact semi-width, times this area, or contact semi-width times its square root. It will appear as a straight line. And again, if we look at the very high velocities, the material will become will behave as glassy, at least around the edge, and hence you will retrieve again an elastic solution, also explained by JKR, but as told before, with a different work of adhesion now that has been augmented by this ratio between the instantaneous and the adiabatic modulus. And in a graph like this is shown by this movement of the curve towards the left. And with these two limits explained, we can start looking at numerical solutions. So in particular, we look at the effect of velocity, as shown here, quite unexpectedly, if you want. It can be seen that for small velocities, we're very close to the adiabatic limit, whereas as velocity increases, we're approaching the glassy limit. And of course, here you can also see a couple of indentations. And it is clear that except for an initial transit period, that accounts for the fact that at the onset of retraction, the velocity of the edge is 0, and then it accelerates. So, but once once this transit has passed, the behavior does not depend on the maximum indentation depth. And let us see now what the effect of the Maugis parameter is. And the first question is, why do we need to study this parameter? Because many times the JKR solution is good enough, and certainly in this problem is. However, even when the JKR solution is good to describe load versus area, it is not good enough to describe viscoelastic effects. And the reason is the following: because as the Maugis parameters increase, this spike will become narrower and taller, and hence the stress rate will also be higher, and hence the material will be closer to the glassy state. So as Greenwood and Johnson pointed out, at the limit of infinite Maugis parameters, at the limit of JKR behavior, the system will always be in the glassy limit, even at very small velocities. And of course, that's not what observed in reality. And hence, we'll always have to count that the Maugis parameter is actually finite. And so we can see here the numerical results, and in agreement with the previous explanation, with increasing Maugis parameter, we're approaching the glassy limit. And of course, you have probably noticed that increasing both the velocity and the Maugis parameter have a similar effect. So the question is, can we use that for our advantage? And the answer is yes. So we can use that to try to estimate how stress rate increases. So if we go back to this previous picture, and you have this stress rate here, and the pressure spike that's given by PA and a certain width. So the pressure rate at any point in the surface will be approximately this ratio here. So the velocity, the retraction velocity, or rather the velocity of the edge, but we're assuming that these are linear related, times the adhesive pressure divided by the width of this contact. And we can calculate that to sort of give this expression for the non-dimensional pressure rate. And then what we can do is to use this to define a parameter, this chi. And these are just 3 different but equivalent formulations of the parameter. And this parameter is gonna tell us whether viscoelastic effects are reasonable or not. And as we see here, it conveys the information that we had before, that for higher velocity and higher Maugis parameter, the viscoelastic effect increase, but also the increase with tau. Because again, a material that's reacting is lower, velocities appear faster, and hence we will be closer to a glassy limit. And so we have here some numerical results where we have different cases where you have here the velocity. For example, if we take the orange ones, the velocity is quite different. The Maugis parameter is also quite different, but the value of chi is actually the same, and hence the response is quite similar. And so from that, we can conclude that this parameter is a good estimator for how important viscoelastic effects will be. And just as an estimate from these results, you can see that for a value larger than 160, we're quite close to the glassy limit, whereas for a value smaller than 2, you only have small viscosity effects and probably can be neglected in practice. So with that, let me conclude. So we have studied the retraction load area curves of viscoelastic materials, which lays between two limits, one at very small velocities and one at very high velocities, and both of them are correspond to an elastic response, but one with one with a given work of adhesion, another one with a much higher work of adhesion. And the glassy limit is approached by both increasing the velocity and the Maugis parameter. And this can be summarized by this new parameter that has been developed, and that can be used to estimate whether viscoelastic effects were relevant or not in a given case. And with that, thank you for your attention, and I hope you have enjoyed this presentation.